Greetings and welcome again to this course on CFD. Today is our third lecture for this week. For the remaining week, we are going to see in detail about time integration or advanced method, arrangement of variables, another important topic what is known as a pressure velocity coupling. There are different methods available under pressure velocity coupling. We are going to see them in detail. So, time integration methods. In the general Navier-Stokes equation, we have considered diffusion term separately, convection diffusion term together, and there is one more important term, that is a time derivative term. So, we have to know how to do that in finite volume strategy as well. The general Navier-Stokes equation is written as shown here, dou by dou t of rho phi plus divergence of rho u phi equal to divergence of gamma grad phi plus S phi, where phi is any property, gamma is a diffusion coefficient and u is a velocity vector. To recognize the terms, on the LH side, first term represent time derivative change, otherwise it is local acceleration. Second term is a convective flux, on the right side the diffusion term or any other source term. So, we perform the time integration on the control volume. After suitable replacement of volume integrals of convective and diffusion term, the CV integration results as shown here. So, you have a time derivative term. So, you go from present time level t by increment in time delta t. So, the integration limit is from t to t plus delta t, and then first term time derivative term integrated within the control volume. That is a new term we are seeing for the first time. Remaining all known before, the convection term, diffusion term or any source term. We can replace in the time derivative term integration over the control volume and integration over the derivative. So, change the order of integration in the time derivative term, that will result in the formulation as shown here. So, this is from time t to t plus delta t. So, there are many methods available. First, we will see two level methods. Two level corresponds to, it involves values of the unknown at two time levels. Under two level methods, we have Euler method, trapezoidal method, predicted character method. Then there is a multi-point methods. Basically, two level methods, you can have a maximum of second order accuracy. If you want to have a higher order accuracy for the time derivative integration also, we have to have some other procedure, and that is multi-point methods. One of the things that we are already familiar is a Runge-Kutta method. You also have a classification what is known as explicit method as well as implicit method. First, we will see in detail Euler method. So, in Euler method again you have forward Euler or explicit method, and that is shown here, phi at n plus 1. Here superscript n plus 1 corresponds to time. So, phi at n plus 1 means phi at new time level, which is defined as n plus 1, is equated to phi at n, that is a old time level with some derivative, and graphically it is shown here t0 and t0 plus delta t, and new value, that is the function here at t0 plus delta t is evaluated from phi at 0 time 0, that is what is shown by this. This is supposed to be the function variable. A function, this curve represent function variation. And a backward Euler or implicit method, which takes the value at the function itself, and that is shown graphically here. So, t0 plus delta t value is uses at n plus 1 value also. Both these methods, that is Euler method is usually, or it is, you can prove that it is first order accurate in time. Why do you have to worry about order of accuracy in time? So, if you solve the Navier-Stokes equation in full, we already learned convection term, diffusion term, discretization of it, and it is possible to increase the order of accuracy for convection term and diffusion term. It is necessary as far as possible the time integration term also of the same order as the spatial derivative terms. Hence, when you solve by that Navier-Stokes equation a particular problem, you can confidently say, for example, it is second order accurate in time, second order accuracy in space. Otherwise, depending on the order of accuracy, you have to make very clear statement. For example, if you use Euler scheme for time integration and second order accurate, any second order accurate scheme for convection as well as diffusion scheme, then you have to say it is first order accurate in time and second order accurate in space. There is another procedure, what is known as a midpoint method, which is also otherwise called leapfrog method, where you evaluate the function at half time level between previous time level and current time level, that is given here as n plus half, and graphically it is shown here. So, value at n plus half is in the middle and phi at n plus 1 using phi at n plus half is used. The leapfrog method, you are able to increase the order of accuracy from first order to second order accurate, and it is also implicit method. How do you obtain all these Euler methods? We have already learned Taylor series of expansion. We had used the Taylor series of expansion to get any order of accuracy difference formula, and we explained only for spatial. They are not actually restricted only for spatial, they are also used for time integration, and that is what you are seeing here. So, in this case y of t plus h by Taylor series expansion is as shown here, y of t plus h f of t comma y of t plus higher order term, and you know that h squared by 2 factorial, second derivative and so on. We are only interested in first derivative for time. So, we suitably replace, then you get different Euler formula. Next is a trapezoidal rule, where this is combination of both implicit as well as explicit, and you have a weightage of half, 50% weightage for the explicit part and 50% weightage for implicit part, and this is also known as semi implicit scheme or Crank-Nicolson scheme. Graphically it is shown here. So, we have a trapezoidal rule. So, T0 at the point is shown here, and T0 plus delta t it is shown here, and you fit a trapezoidal curve, you have a trapezoidal fit between the two, then you get this formula derived. It is explicit 50%, implicit 50%. So, this is called semi implicit, and it is a second order accurate in time. Let us look at some details about explicit method. They are conditionally stable. We already learnt about stability, von Neumann stability analysis. Hence, all the explicit schemes are conditionally stable. There is a criteria called CFL criteria, that is either you have a limit on delta t or you have a limit on delta x. We are dealing with the time integration method. So, there is a limit on delta t. Large delta t is sometimes preferred for a problem you want to capture different scales, then you want to have large delta t. Okay. It is easy to program because current level values are not required, all the previous values are only required, and you do not have to work hard to write a very difficult program. It is less computational time. For every step it takes only less computational time and less memory per step. If you look at graphically the explicit method, so value at n plus 1 is evaluated based on variable value at nth level from I minus 1, I and I plus 1. Let us look at implicit method. all the implicit methods are unconditionally stable. That means you can afford to use any delta t. It usually follows iterative solution for every time step. Explicit method, one inversion is enough, whereas implicit method requires iterative procedure because it accounts for the variable value at the current time level also. It is relatively hard to program as compared to explicit method, and it takes more computational time as well as memory for every step. Graphically it is shown here. So, value at n plus 1 is evaluated based on value at n plus 1, but at I minus 1 as well as I plus 1. Let us look at the performance of this explicit scheme, implicit scheme, and the role of delta t in explicit scheme. Already there is a problem considered, that is unsteady one dimensional heat conduction example problem. We take this problem, it is already solved, it is only a demonstration to show the effect of time step as well as to understand explicit implicit method performance. So, what is shown here is a time, is a distance and temperature for one particular calculation, results obtained after 50 seconds. If you use different delta t, performance by explicit scheme, and what is shown here is if you use time step of 10 seconds, that is delta t is 10 seconds, it is slightly larger, right. When you have an explicit scheme, delta t matters because it is conditionally stable, and in this example we show two different delta t. One is delta t is equal to 10 seconds and delta t is equal to 1 second. So, which is a smaller time step. An exact solution is already known for this problem, that is already plotted, and if you use delta t 10 seconds, after the calculation has proceeded 50 seconds, you see performance, there is a wiggle, okay. It does not reach exact solution, it goes up, it goes down, it never reaches the exact solution. If you use delta t 1 second, that is finer delta t, then you see performance, it reaches almost same as exact solution and performance is better. So, in the next plot for the same problem, if you happen to incorporate implicit scheme and you see the performance for the same final times 50 seconds and then one delta t, that is 10 second, we already noticed explicit scheme, it shows stepwise solution, whereas implicit scheme it captures almost same as exact solution. So, you understand the effect of implicit scheme as well as explicit scheme on the results. You also have to see the time required to obtain the solution as well as memory required to use explicit scheme or implicit scheme. So, the question is whether you can combine both implicit scheme, explicit scheme, because each of them supposed to have some advantage. And solution at new time step is predicted by explicit scheme, and then in the next step it is corrected using an implicit scheme. So, such kind of two stage procedure is called predictor corrector method. So, one proposal is given here, new time level is predicted by explicit scheme and it is corrected by implicit scheme. For example, predictor step, because it is only predicted, it is not the exact value, we use a superscript star. So, phi star is phi of n, phi star equal to phi of n plus f of t n phi n delta t, and this we already know it is a forward Euler or explicit scheme, and star superscript star indicates temporary value or predicted value, and this will be corrected using a trapezoidal rule, and that is what is shown here. So, when you use a trapezoidal rule, the predicted value becomes known value, and that is what is suitably used here when you write down the explicit part and when you write down the implicit part. Okay, this is what is known as a corrector step. Okay, this method of 2 levels, and it is second order accurate in time. In 2 level scheme, highest order achievable is delta t squared. Order of method is not the sole indicator of its accuracy. The order only determines the rate at which error goes to 0 as the step size goes to 0. So, the order, it is not just indicator of accuracy, even if you increase the order determines the rate at which error goes to 0. So, if you decrease the delta t, and we have already seen in the results, if you have a delta t, very high delta t, the performance by explicit scheme is poor, but the same explicit scheme performs better if you reduce the delta t. So, for small enough size, a higher order method will have a smaller error than a lower order one. If the step size is small, then one can estimate the discretization error in the solution by comparing solution obtained by 2 different step size. So, it is possible to get an idea of what is the error in the new delta t, and that procedure is what is known as a Richardson extrapolation procedure. So, we have seen you have a 2 level method. The 2 level method, highest possible accuracy is second order accurate. The question is now whether it is possible to devise a scheme to have higher order accuracy even for time derivative term. I already mentioned when you solve a Navier-Stokes equation full, you have a convection term, diffusion term, pressure term, or any other source term, and we know very well how to obtain different higher order accuracy for all these terms which are spatially derivatives. We have to have a corresponding higher order accuracy possible even for the time derivative term. So, overall solution can be called of the same order of accuracy both in time as well as in space. So, we are going to look at procedure how to obtain higher order methods even for time derivative, and such a scheme is also known as a multi-point scheme. In multi-point scheme, as the name indicated, we use more points. Now, how do you obtain these more points? These additional points are either already computed at previous time level. So, for example, you are at current time level n plus 1, you have values at n just immediate previous time level. You also have a value at previous time level n minus 1 or n minus 2. So, this is one possibility, or the difference between time n and time n plus 1 can be divided into number of points, and values can be computed at these intermediate points. Such a scheme is also multi-point method. It is called accordingly multi-point methods, and there are multiple options available. We already know a method called Runge-Kutta method, which is a multi-point method. One example of multi-point method is shown here, what is known as the Adams-Bashforth method. Here again you have one predictor as well as one corrector. So, phi at n plus 1 is phi of n plus delta t by 2 3 times function evaluated at time level n and 1 time function evaluated at n minus 1 level. Then this is actually one step which is second order accurate Adams-Bashforth method. It is also possible to increase even in Adams-Bashforth method next level, there is a third order accurate by considering one more additional points at much previous time level. So, the formula is finally shown here, phi at n plus 1 is related to phi at time level n, then phi at time n minus 1, then phi at time n minus 2. So, n is a just immediate previous time level, n minus 1 is 1 before, and n minus 2 is 1 even 1 before that. So, by considering more points in the previous time level, you are able to construct a method. This is what is known as the Adams-Bashforth method. And how do you obtain these coefficients 3, 23, 16, 5? I already mentioned, by using a Taylor series expansion even for time, then you are able to construct these methods. So, the first one uses only immediate previous time level, it becomes second order accurate. The second one uses 2 time levels before, it becomes third order accurate. One more observation, all these uses previous time level, hence it becomes explicit scheme. So, Adams-Bashforth scheme, you are able to obtain explicit second order as well as third order. The next one is what is known as Adams-Moulton method. In this, the second or third order accurate scheme is shown here, which consider values at time level n and time at n minus 1, and then one more point which is at the present time level itself, that is time at n plus 1. So, time at n plus 1 is a present time level, and variable value at that present time level is used because it is also there on the left hand side. So, this scheme is implicit scheme. So, you can actually construct like this to get any order of accuracy, multi-point level, explicit, implicit or combination of both. A common procedure is to use m minus 1 order of Adams-Bashforth method as a predictor and mth order of Adams-Moulton method as a corrector. So, we have already seen Adams-Bashforth method 2 scheme, second order accurate, third order accurate. Adams-Moulton method 1 scheme, third order accurate. So, you can combine both in the form of predictor as well as corrected methods. You can use these Adams-Bashforth, Adams-Moulton method independently. You can also combine both of them in the form of a predictor as well as corrector method, and that is what is shown here. Sorry, that is what is described here. You can use one order lower Adams-Bashforth method as a predictor and the one order the desired order as a corrector. It is easy to construct any order of accuracy by this Adams method. Only one evaluation of derivative per time is possible. The disadvantages, if you start your calculation say time is equal to 0, then you do not have values at the previous time level n minus 1, n minus 2. So, any of this method Adams-Bashforth method or Adams-Moulton method are not self starting. So, one has to resort to any other previous completely explicit method to get first value either at n minus 1 or n minus 2 before switching it to Adams-Bashforth method or Adams-Moulton method. So, your initial calculations are not accurate enough. So, in this class we have seen different time integration procedures, explicit method, implicit method, influence of explicit method, implicit method for a illustration problem, influence of delta t on the performance by explicit method. Then we also learn how to get higher order accuracy for time derivative by predictor corrector method, and we showed Adams-Bashforth method and Adams-Moulton method and how to combine them also. Next class we will see another interesting topic. Until then, have fun. Thank you.